Okay, wow, the best. Great, it's just like my face. Okay, good. So welcome to the class. What we will do today is we will talk about community structure in networks and detection of communities in networks. So here is how this relates to what we have talked on Tuesday. On Tuesday, we talked about this idea of identifying structural roles of nodes. We talked about how networks are composed of little subgraphs, and then we talked about how you can represent the role of a node through this graphlet representation, and how you can now cluster the nodes. And nodes that kind of have a similar structural role in the network will be clustered together, even though they might be in very different parts of the network. Now, for today, what we will talk about is this notion of community structure in networks, where community structure in networks, you can think of it essentially as identifying sets of nodes that are densely connected with each other. So it's really identifying clusters, partitions, groups, communities inside networks. And conceptually, the way we think of this is, here is how we would like to think of networks for today's lecture, right? What do I mean by this? We would imagine that, let's say if this is a social network, that there is a set of social communities that are more connected with each other than they are connected to the rest of the network. And our goal will be to automatically identify these types of tightly knit communities. This is a nice conceptual picture to have in mind. But what I would like to show you first is some motivation from social science that gives you kind of proofs why you can think of networks as having this kind of cluster-based organization that we will then learn about methods to extract this organization out of the network. Okay? Here is a question that is, I think, the lesson from here will be important for life. You will see why. Okay? So the question the way this story starts is to say, how does information flow through networks? And what kind of distinct roles do nodes play in the flow of information through these networks? And in particular, we will be asking about the role of different types of links or edges we have in our networks that allow for flow of information. And there was today a very famous sociologist, professor here in sociology department at Stanford, Mark Granovetter, who was doing his PhD thesis in the 60s. And he was interested about how do people find information about new job openings. So he went around and was asking people, how did you find about your job that you are holding right now? And then the question was, how did people find out information about the job, and what role did the social network play in this? Right? And what he found out when he did his interviews is that the way people find about jobs is through acquaintances rather than close friends. Right? You would imagine that if I have these close friends, they're really there for me. I meet them every day, every week. They really try to help me find my job. But when he did the interview, what he found out is that when people find a new job, they find it through some acquaintance that they very rarely meet, and so on. So this is very surprising, right? You'd expect your close friends will help you, but if you ask, okay, how did you find about your job? People said through a casual acquaintance. So the question is why? Right? Why wouldn't your friends help you, or why interacting with your helps doesn't help you learn information about the new job? And he came up with this explanation. Yes?
Sorry, so did he consider the number of acquaintances? Like you have more acquaintances than you have close friends, right?
You can imagine that there is about the number, but even if you control about the number, there is something more fundamental about just the number. Okay, and here is his explanation, right? He said that there are two perspectives on a link in the network. There is a structural perspective, in a sense, what parts of the network does this link connect? And then there is the interpersonal perspective, where he says, is a link to some person, is it strong, which means it's a real close friendship, or is it a weak link, which is the kind of casual acquaintance type link? And he came up with this explanation to say, okay, how does this structural and interpersonal relationships type of a view of a link, how do they relate to each other? And he was basically saying the following. Another thing we have to resolve is this notion of triadic closure in networks, right? If I have a person A, I have a person B and a person C, you can ask, is this type of edge, how likely is this edge to happen? How likely is that edge to happen? And as we talked about clustering coefficient and so on, the edge AB is much more likely to happen than edge AC, because AC kind of goes 3 steps away in the network, and A and B have, let's say, 2 friends in common, so this edge is likely to happen, as I will show you next. So Granovetter's theory is named the strength of weak ties, right? That kind of the value of these weak ties that you get. And he was saying the following. He says, the first point he makes is structural, kind of the structural argument. He says, structurally well-embedded edges are also socially strong, right? So and he says, the long-range edges that span different parts of the networks are socially weak, okay? And then he makes the information argument. He says, the second point is that long-range edges, acquaintances, allow you to access information in very distant parts of the network. And structurally well-embedded edges are, in some sense, heavily redundant, in a sense that in terms of the access to information. And if I go to this little picture here, if you think about node A, and the argument is the following. These edges are very redundant, right? Because anything I hear from this person, I can also learn from that person. But these are the edges that are socially strong. And then these types of edges that allow you to access to some other distant part of the network, they are socially weak, but they allow you long-range kind of connection, right? And he was making this argument that, yes, why you don't hear about new jobs from your close friends? Because in close friends, you kind of knit in these cliques, and these edges are very redundant, right? And really, edges that are rich with the information they bring to you are these long-range edges. But if this is the case, then you see now that we have this kind of clustering structure. We have a clique of strong interpersonal relationships and a few long-range edges to another, let's say, clique of strong interpersonal relationships. And that's kind of the explanation he came up with. So the point is that this triadic closure in networks, which basically means that people who have a friend in common are more likely to create connections, is very pronounced in social networks. For example, if you say, if A and C have a friend in common A, why should they create a connection, right? First is A and C are more likely to meet because they have a friend in common. B and C will trust each other, again, because they have someone in common, right? And the node A has an incentive to bring B and C together so all of 3 of them can hang out, rather than, you know, the friend A has to first spend one afternoon with the friend B and then another afternoon with friend C. They can all kind of hang out together, right? And just to show you that this triadic closures is important, there was a very interesting paper a few years ago by 2 sociologists who, for example, showed that for teenage girls in the social networks, if their clustering coefficient is low, so if they don't have a lot of triadic closure, which means if they have friends who don't know each other, but they are kind of just this, like that in the network, you know, they are more likely to contemplate suicide in this case, right? So triadic closure really matters. And the other thing that matters is having these long-range edges really matters for you to have access to different distant parts of the network to gather information from them, like job openings, right? So weak ties are extremely important for job openings, and many of you will be graduating. That's the life advice. Okay, so nurture your weak ties. Okay, great. So that's the life advice. Now, this was a very nice sociology explanation in 60s, super influential paper. I think this is the most cited paper in all of social science, but it was very hard to empirically validate. And it was only in 2007, so I don't know, 50 years later, that this was able to be verified, this theory. And the way this was done was on a set of cell phone communication graph, right? From a, let's say, anonymous European country where they had about 20% of country's population and the cell phone calls between them. And they said, let's say that the weight of the edge, the strength of the friendship, equals the number of phone calls we have between us in a, I don't know, in a week or in a month, right? So the more we call each other, the closer friends we are. Sounds like a reasonable definition. So this is now the strength, interpersonal strength of the friendship. Now they also want to define the kind of structural strength of the friendship. And they came up with this notion of edge overlap. And the way this edge overlap matrix works is here, but it's essentially for a pair of nodes, Vi and Vj, it measures out of the friends they have, how many of friends are mutual. Okay? So it's essentially number of neighbors of the one node, union, intersection number of neighbors of another node, minus the two nodes themselves, divided by the union of their neighbors, again, minus the two nodes themselves, right? So the idea is that here, if the network, if the nodes I and j are connected this way, then the edge overlap is 0. If I and j are connected this way, then the edge overlap is 1/3, because they have 2 friends in common out of 6 total friends. You know, here it would be 4 friends in common out of 6, so it's 2/3. And here, for these 2 nodes, right, all the friends they have, they are common friends, so this is overlap of 1, right? So the way to think of this is a structurally very strong or very embedded edge, because it has all these redundant friendships, and that's a very structurally very weak edge. It's almost like a bridge edge, because it connects to different parts of the network that have nothing in common, right? And what Granovetter would predict, what his theory would predict, is the following. He would predict that for edges like this, people call each other all the time, and he would predict that for edges like that, people don't call each other very often, right? This is now the structural version of a strong tie, and then this is a interpersonal version of the strong tie, right? Interpersonal is number of phone calls, and the embeddedness is the structural version of strength. And he says the two are connected, right? So this is a weak tie structurally as well as personally, and this is a strong tie structurally as well as personally. Okay, it's a redundant tie in some sense. Okay, is this clear? It's clear that why Granovetter makes this prediction? Yeah. So now let's look at the data. Okay, so here is how to think about this. So the x-axis is number of phone calls. So it's the interpersonal strength of the friendship. These are super close friends. I guess, I don't know, my mother or your mother would be the strongest friend you have under this definition, right? And these are very weak acquaintances, weak friends, right? And then what they show here is the overlap, right? Overlap on the left, think of this, and on the right, think of that, right? And he showed, like what you see here is this correlation, dependence, which means that the stronger, the more phone calls you make, the higher the friendship overlap there is, right? And what is the red line is under the null model, where the network structure is the same, but the edge weights, the number of phone calls, is kind of randomly assigned. And of course, if you do that, then there is no dependence between the strength, the number of phone calls, and the overlap of the edge, right? So we want this to be flat. If we destroy it, it's not there. But here you notice this strong relationship between interpersonal strength and structural strength of the edge. Okay? So this is the test that this theory is true in social networks. To give you another, perhaps more striking visualization of this, this is one small part of these social networks of phone calls, where the color indicates how many phone calls are there between a pair of people. And you see that red, which means very high number of phone calls, is kind of clustered in these little regions, right? And you notice that these other edges are kind of green and yellow, so they are much weaker. And this is one way to see it, but a very striking way to see it is to say, how would this network look like if I visualize it the same, but I randomly permute edge strengths, right? So I would randomly assign, I would say I have, I don't know, 700 red edges, let me just randomly color them. And then I have 400 yellow edges, let me randomly color them, right? And if you do that, this is how this looks like, right? So if the strength of the number of phone calls would be independent of the network structure, this is how the network should look like. You see that now these long-range edges, lots of them are red. In reality, the network looks like this, right? So all the strong edges are kind of clumped together into these clumps, and then basically between these clumps, it's all yellow and green, right? So this is the important thing. Another thing, so now we kind of verified Granovetter, but we would still like to see does our network have these types of clustering structure? So if our network has this clustering structure, then the idea that this experiment tries to solve is the following. It says, if I take strong edges, edges by the number of phone calls, and I remove them, then these edges should be here inside, and I can remove a lot of them, and the network will still be connected. But if I remove edges that have low strength, low number of phone calls, these edges should connect different clusters. So if I remove those, the network should fall apart very quickly. Right? That's the hypothesis. And this plot is trying to test that hypothesis. We start with the full network that is connected. So the y-axis is size of the largest connected component. We are removing edges one by one, and we are looking at how the connected component gets destroyed. Right? And what is the point here is that red is removing edges from high number of phone calls to low number of phone calls. From low number to high number. And the black one is from high number to low number. And what do you see from here is that if I first remove the low number of phone call edges, the size of the connected component decreases faster than if I first remove the strong edges. So it means that if I first remove these guys, the network will fall apart faster than if I first remove those edges, right? And this is just based on the strength, number of phone calls, right? If I can do the same thing with the overlap, if I do this based on overlap, the difference is even bigger, right? If I remove low overlap edges first, the network will decompose into small clusters much faster than if I remove high overlap edges first, right? It's clear if I remove a high overlap edge, the network will still be connected, right? So what does all this evidence point to? It points to conceptually to this type of picture where I have these clusters, I have these weak ties that are weak in terms of phone calls and are weak in terms of edge overlap, and then I have these kind of clumps of densely connected nodes where I have high interpersonal strength of communication, and I also have high overlap, right? So this is what I wanted to tell you from kind of motivation for why do we believe networks have clusters, and some empirical studies that have validated this on the social networks, but the same happens also in other types of networks, like in biological networks, where you can think of this as like if you think of biological networks as some kind of machine, then these are almost like functional modules or subparts of the machine that are in charge of a given task, and you see similar types of structures. So this was the introduction to today's lecture in 20 minutes. So now let's actually talk about what we'll really talk about today. So we'll talk about community structures and how do we discover them, right? So what this theory that I showed you so far, or this evidence from social science, tells us that a good conceptual picture of networks is like that. And then what we'd like to do is we'd like to be given a network and we'd like to identify these communities, right? And when I say communities, you can think of them as clusters, groups, modules. I'll be using these terms interchangeably. And for all of them, essentially, our main intuition will be that I want to identify a set of nodes that has a lot of internal connectivity, a lot of edges inside the set, and a few edges pointing outside the set, right? And this is what we'll try to formulate now mathematically. The question now is, how do I automatically detect communities or these clusters? What I try to show with this visualization that you can have quite interesting structures, right? If you look at this, is essentially 3 groups where each group internally is decomposed of a couple of different groups, right? So you can have this kind of hierarchical structures and so on. And the first place, one of the famous examples where this community structure came out to be is this Zachary Karate Club network that has very rich structure. And again, this is social sciences. I think this was maybe even sooner, maybe in 1950s. And this is a network of 34 nodes. And the story behind this network is the following. So Zachary was, again, a PhD student. He was doing his PhD, and he was studying friendships in this karate club at some university. And what happened during the course of his study, there was a big quarrel or a fight between the members of this karate club. And what happened is that, that the karate club split in two. There were two newly formed karate clubs. One was formed by a very influential person, and another one was formed by the instructor. And it turns out in this visualization that I think 34 is the instructor, and number 1 is the guy who decided to split. And circles and squares tell us who decided to join which club. Okay? And what should be striking here? If you look at this graph, you see that it actually predicts, its structure predicts who will go where, right? If you look at it, are there groups? You kind of see from the social network there is quite a lot of connections between the nodes on this side, and there's quite a lot of connections with the nodes on the left side, and there is relatively few connections across. And if you say, what is a way for me to cut this network in half and cut the fewest number of connections? This is the cut that almost perfectly predicts who will join what karate club and who will join what other karate club, right? And this is kind of one of the first evidences that the social network structure has predictive power of saying who will join one club versus another club, right? Essentially says what are the decisions people make, where to train karate or whatever else, right? I wanted to show you this because you'll see this Zachary's Karate Club network everywhere. There's even an award. There is a conference where whoever first mentions this keyword, this network, gets this kind of, I guess, shameful medal for being the person who did that. But there are many others more interesting networks. Another place where these kinds of communities arise is, for example, if you look into sponsored search or web advertising. The way web advertising works is that you have advertisers who bid on keywords or queries, right? Whenever a particular keyword is entered, this particular set of advertisers want their ad to be shown. And you can think of this as a bipartite graph, and you can think of identifying tightly connected clusters in this graph, which would mean find me groups of advertisers that are interested to bid on the same queries, right? And if you do that, you start identifying essentially groups of advertisers that are interested in the same area. This, I think, was work coming from either out of Google or coming out of Yahoo, okay? So that's another way how you can think. Another thing we learn from this is if I plot these types of adjacency matrix, then a cluster that I had here represents to a kind of a clump of densely connected nodes, right? It's kind of a set of dots that have this kind of block diagonal structure, and that's what we are trying to identify. And then the last thing I'll show you, this is a very striking example. So this is a network where every team is an NCAA team. So NCAA, the way I understand, is this league of American university football teams who are playing against each other. So every dot here is a football team, and an edge means that the two teams come and play each other. And I can ask you through this visualization, do you see any clustering structure, right? And it's debatable whether it is there. But if you go and apply the methods we'll talk about, you identify the clusters. Here they are, and what is interesting is that these clusters exactly corresponds to the divisions or conferences inside this NCAA competition. And what's maybe even more interesting is that you have these blue dots that don't seem to belong to anything, and then you say who they are, and there is, you know, a conference called independents, right? So these are essentially teams that are not part of any conference and they are not part of any cluster. But you see that we basically perfectly identify the clusters. The only mistake, right, is here and then this one, right? So we basically make a few mistakes, but the rest is perfect. And if I show you this network, you could have never done it yourself, right? It just seems some random pattern, but it's not. It has this kind of very well-defined clustering structure, okay? So this is what we are trying to do. So on the input, we get this. On the output, we'd like to identify these clusters. So now let's start defining how do we do that. So what we want to do is identify this set of tightly connected nodes, and we will define this notion of modularity, this metric Q, that will be a measure of how well is a network partitioned into communities. And first, I should define what a partition is. Partition is just you take nodes of the network and you split them into groups such that every node is a member of exactly one group. That's called a partition in mathematics, okay? So we want to assign every node to exactly one group such that we try to then measure how well did we discover the clusters. And the idea is that we wanna do this such that we say that modularity Q will measure the following difference. It will say, how many edges do I have within the group I discovered, minus how many edges would I expect between the members of the group, okay? And if this difference is big, then I have found a strong group, because it has a lot of edges inside, and it has actually many more edges inside than what I would have expected, okay? So it's an unexpected cluster in this respect, right? And of course, what's the common theme from the previous lectures? Whenever I say expected number of edges, I need a model. I need to say, what would I expect? If there would be no clustering structure, how many edges would I expect between this clump of nodes? And if I see many more than what I would expect, then I'm like, wow, I found some interesting deviation from randomness. I'm excited. Dear user, here it is. Okay? So now let's define the null model. And this null model we'll define today is it's a version of the configuration model that I talked about last time when we talked about motifs. And the idea here is that we can actually do this analytically, right? So imagine we are given a real network G that has n nodes and m edges. And we would like to construct a rewired version G prime, right? That has the same degree distribution, but connections are there uniformly at random. And you should remember, on Tuesday I was showing you this thing where I said, every node has a number of spokes, that is its degree, and I want to randomly connect these spokes. That was my answer on Tuesday. Today we will extend this answer and say, let's consider this random graph with a fixed degree distribution. Let's consider it as a multigraph. If you remember the first lecture, multigraph is a graph where I allow multiple edges between a pair of nodes. So then the question is, under this model, under the multigraph, how many edges do I expect to see between a pair of nodes, right? And it turns out that the expected number of edges between nodes I and j, where I has degree k sub I and j has degree k sub j, is k sub I times k sub j divided by 2m. And the way, right, and if I put this together, it's basically the product of the degrees divided by 2m. So let me first explain how do you derive this equation, right? The way you can say is the following. This guy has k sub I spokes pointing out. What is the total number of spokes available for me to connect to? It's 2 times number of edges, right? The important thing is the sum of the node degrees is twice the number of edges. Because if I sum up the degrees, then every edge gets counted twice, right? There's kind of the one endpoint and there is the other endpoint. So the sum of node degrees is twice the number of edges, right? So that's why I have this thing here. So out of all the available endpoints, my target node has k sub j of them. And I get, node I get k sub I attempts to hit any of these things. So in expectation, I will hit k sub I times k sub j divided by 2m, right? That's the expected number of edges if edges go randomly between a pair of nodes with this type of these types of degrees. Another side calculation you can do is that if this is correct, then if I sum over all the node pairs, then the expectation of this thing should be exactly the number of edges I see in my graph. And this is what I try to do here, right? I say, let's go over all pairs of nodes I and j, and for every pair, I has some degree, j has some degree, divided by 2m. That's the formula there, and I have 1/2 because again, this will be every node will be counted twice. So this together should be the total number of edges in the network. And if I work out the sum, what can I do? I take this 2m out. I can take the sum over j and take the sum over I on this side. So this is what I did here. I took 2m out and I kind of pushed the summation over j inside. So this is now a summation of node degrees of all the nodes. And then I multiplied that with the degree of the node I, and I sum over all the nodes I. Now I know what this is. Here it is, right? So this is 2m. So I'm here. So this part is 2m. And then if it's a constant, I can take it out. And then this part is also 2m. So what I get is 2m times 2m divided by 4m. 4m comes that I have a 2m here and another 1/2. So I have 4m divided by 4m squared. Sorry, I have 4m squared divided by 4m. I can cross things out, and what survives is m. So this shows that this kind of further verifies that this formula is correct. Okay, good. So now I told you how to compute the expected number of edges. So now let's go back to the modularity formula, right? We need to say how many edges are within the group S, how many edges do we expect to be between the nodes of the group S. So here is the formula, right? The modularity of the graph G and some community partitioning S is the following. This is the normalizing factor. Then I sum over all the groups, all the communities. For every community, I ask how many, these are the pairs of nodes that belong to the same community. This will count how many edges are there between those nodes, and this is the expected number of edges, right? And this is now called modularity, right? So this is the normalizing constant, so that modularity will have a range between -1 and 1. Aij is 1 if I points to j, and it's 0 otherwise. And this is the expected number of edges, right? So what I did right now, rather than first computing the number of edges minus computing the number of edges, for every edge I'm saying is an edge there and how many edges I would expect. And then I sum this up, and that is my modularity. Yes, great, yes, I was waiting.
Modularity considers also self-loops?
Modularity would consider self-loops as well. It's in this multi-graph regime where you can, yes, link to yourself as well if you like. That's the null model for this thing. Of course, you could try to come up with more advanced null models, and what would change is this term would change. Good point, yes?
For all of these, are we doing approximations because the graphs are big? Because it just seems like every time we make a connection, we don't take out the connection from our formula, like on the previous slide.
So the previous slide was kind of the calculation was in expectation. And that's the only thing to do these things analytically. You could do them simulation-wise, but it's not clear how you would do that and why would you want to do that, right? So you can come up with some way to say how many edges or how likely is an edge to be there. And the idea is that modularity defines number of edges you see minus number of edges you would expect under some model. Now, if your model is simple enough, you can derive it. But if your model is not simple enough, you could simulate it. Nobody does that, but you could. Aha, how I got this thing? Yeah. How to think of this? As you go sum up here, this will sum up to 2 times m, right? The total number of edges, right? So if and then this will be whatever it will be. But in the worst case, this summation will go up to 2m, right? So this means that if I divide by 2m here, I'll be between +1 and -1. All right, good question. Yes, go ahead.
So how do you think about values of q? Is it that if it's more negative, it's a good partition, or
Oh, great question. Yeah. Super question. Yes, we didn't answer that. So this is between 0 and 1, right? So how do you think of that? Right, here is how to think of it, right? Modularity will take values between -1 and 1. If the number is positive, then it means I see many more edges between the members of the group than what I would expect under this null model. And what people usually say is if your modularity is between 0.3 and 0.7, then you have significant community structure. Of course, if it's 0.95, it's even better. But in practice, these are kind of the ranges of the value that people have seen. Now, of course, what your question also is what happens on the negative side? What if it's negative? What if it's negative? It basically means you identified anti-communities, right? You identified sets of people that don't link with each other even though they should. So in some sense, you could imagine that you found enemies or clusters of enemies that have high degree. Under your model, there should be links between them, but there are not. So you could even, for a certain application, want to minimize modularity. What we want to maximize it to find the groups, but you could try to flip it if that would make sense for your application. So that was a good point. Thank you. Yes?
In graphs with anti-community structure, does that mean there have to be communities, or is that not required?
So the question is, in graphs with anti-community structure, would there have to be communities? That's a good question. I don't think so. I don't think so. So it's not that I don't think you can show. That's a good question. I actually don't know. But at least my intuition is that you cannot say if you found something with modularity of, I don't know, -0.5, that if you kind of flip everything, you can find something with modularity 0.5. So this is not just, one is not the dual of the other. They are different. That's my intuition. It's a great class project to do it and figure that out and so on. Okay, good. Let me continue. So now we know how this thing is defined. And here I'm just showing the same formula again. Another way how people would sometimes like to do it is rather than having a summation over all the groups and then over all the pairs of nodes in the group, they say, let's just sum up over the entire adjacency matrix, where we will take the same term as I have up there, like here, but let's have this indicator function that essentially returns me value of 1 if nodes I and j belong to the same group, and returns me 0 if they don't belong to the same group. So this summation is the same as up there, just here I'm kind of using this indicator function that tells me is a pair of nodes in the same group or not. Okay, and these C's are basically some variables that keep track of who's part of which community. Okay, so now what do we know so far is if somebody comes to me and says, hey, I have these great communities to sell you, you can say, haha, I won't buy them yet. I will compute modularity, and then I will know are you a crook or not, right? So nobody can now, sell you bad communities. You know how to evaluate that, right? But what you don't know yet, you don't know how to find them. Right? So now what we want to do is figure out how to find them. Okay? So how will we find them? We will try to find partitioning that maximizes this modularity. And here is a heuristic algorithm that works really well in practice, and it's very fast. And its runtime is of the order n log n, where n is the number of nodes in the network. So it's very fast. It's like quicksort. Quicksort has the same complexity, right? And the idea here is that this will support weighted graphs, and it will provide us with hierarchical decomposition of the graph into communities. So what do I mean by hierarchical? Here is what I mean. If you think of this network that I show you here and you want to identify communities, you could say, there are these 4, but then at the one level up, there are these 2, and then there is the entire network. And the way you represent hierarchy is using a dendrogram. Dendrogram is this type of tree hierarchy where at the bottom there are all the nodes, right? So these 3 nodes represent this community, these 3 represent that one, these 3 this one, these 3 that one, and they all represent one community. Then at the next level you have 1, 2, and this lonely guy, so 1, 2, and this guy that represent another one, and the same here, right? So you can represent this community hierarchy using a dendrogram. That's the point here. So now let's see how are we going to discover this kind of nested hierarchical community structure using this Louvain method. The Louvain method, the idea is, the overview is the following, is that this will be a greedy maximization of the modularity score, and we will have each pass of the algorithm will have two phases. In the first phase, we will optimize modularity by doing local changes to node community memberships. So essentially what this means is we look at the node and say, if I move this node from this community to any other community, will the modularity increase? And if the answer is yes, I will do that. And I will keep doing that until no good move exists. And after I have kind of finished that part, I will then go and say, aha, I found good communities, and I will apply the coarsening stage, where basically I will take every community and kind of combine all the nodes into a single supernode. And I will create the new network that is coarsened. And then we will go and apply phase 1 on this coarsened network. So here is a visualization. I start with a network, and I apply phase 1 to identify some groups. Okay? And the way I do this is as I will explain, I start with every node belonging to their own community, and then I try to move nodes across communities to increase modularity, and I keep doing that until I get stuck. After I have identified the communities, I do the community aggregation, which is the phase 2, which means that every set of nodes of the same color, of the same community, gets kind of merged into a supernode, and then I create a graph on the supernodes. And now I can run the same phase 1 on this graph of supernodes, and that will further kind of identify groups, right? So the idea is that for this input network, I have 4 communities at level 1, and then I have 2 communities at level 2, right? That's the idea. This is how we'll do this hierarchically. So now I want to tell you about the first phase, which we will call partitioning, and then the second phase, which we will call aggregation. Yes?
It seems like the order in which you are doing phase 1 would affect the outcome. Is there a heuristic for which order you should proceed through the nodes?
Great. I have a note here. Note that the output of the algorithm depends on the order in which the points, right? Great question. So I was anticipating it. I will explain when I come to here, okay? Great.
Just to clarify, so in this case, you can still use whatever expected model you want at all times, right?
Correct.
You can define it however.
You can define it however you want, right? Like the configuration model I defined is good for undirected graphs, and it allows you also to work with weighted undirected graphs, right? Because it just worries about these weighted degrees and says under the multigraph model, how many edges would I expect? And this is by far the most common null model people use. If you have a network from some domain where you think you have a better null model, that's great to use. What is the benefit of this simple null model is that you can analytically compute the expected number of edges. It's just the product of degrees. So you can do this. It's amazingly simple and scalable. And anything else that is more involved would be much harder, because this is kind of the most inner loop of computing modularity. So that operation, how many edges do you expect within a pair of nodes, get executed essentially for every pair of nodes. All right? Good question. Yes?
How do you define that one null model is better than another null model?
You cannot define that one null model is better than the other null model. A null model, it always depends on what are you asking or what data you are looking at, right? Because with a null model, your goal is not to fit the network as best as possible, but your goal is to find a reference point. Right? And a reference point is different based on the question you are asking. Right? A null model could be like, you say, how do I compute population average if you are a social scientist? If you are interested in a certain question, you will select a certain type of population. If you are interested in another question, you will select a certain type of subpopulation. And now it's not saying that one type of subpopulation is better than the other type of subpopulation. It all depends on the question you are asking. Okay? Good question. That was important. Okay, good. So back to our algorithm, phase 1, partitioning. What happens? So here we start that every node belongs to a distinct community. So every node will say, I'm my own group, I'm my own community. And then and now we will loop over the nodes, and for every node I, we will perform two calculations. We will say, what is the modularity delta if I take the node out and put it into the community of some neighbor j? Right? For every neighbor, I will ask, what is your community? How much would the modularity increase if I take I and put it into j? Okay? And then after I have kind of asked every of the neighbors j of node I, how much would the community membership modularity increase if I move that node I into that community, I will decide on the move that gives me the largest gain in modularity. Okay? Yeah? Everyone happy? Yes, yes. Okay. So, and I keep doing this until I can gain anything, right? So for every node, I look who are the neighbors. I ask every neighbor what part of the community are you, what community ID are you? What happens if I were to join that community? How much would modularity increase? I take the second guy, I ask what community are you? If I join that community, how much would modularity increase? And I keep doing that. And then I join the community where this increase in modularity is the largest. And few things to note. First is that this phase will stop when local maxima in modularity is attained. So whenever no local move, no individual can move to improve the overall modularity. So this is the greedy step. And then the second thing which was a good question before, is that the order in which I process the nodes will also determine the outcome of my optimization. And what generally research papers have shown, that the ordering of the nodes when networks are large does not matter that much, and you can take them, let's say, in random ordering. So people don't pay too much attention to this, at least historically. Yes?
Do you actually try to hit a local maxima, or do you just get like some small Q, or some small delta Q? Because it's possible that like the small changes might never actually converge.
I don't think it's possible that small changes will never converge. I'm happy to talk offline, but I don't see why they should, right? Because if I'm only interested in a delta that's positive, then I will never take a step back. And the only way things wouldn't converge is that my deltas would get kind of smaller and smaller and smaller over time. But I'm working with a discrete system of finite size. So there will always be some minimum delta by which the modularity will increase. So I'll always get stuck. So I'll always converge. Okay? Happy to talk more offline. Yes?
I'm trying to understand why the runtime the algorithm is O n log n. So at this phase, for each node, how much work are we performing asymptotically?
We are performing something that is proportional to the degree of the node. Okay. Right? Like here, I'm saying for every node, let me do this. And I will loop over the nodes several times. Right? So the most expensive thing will be the maximum degree, right? And the most expensive will be the first phase. Everything, the graph will shrink, will be much easier. Okay. Good. So now the question is, how do you compute this delta Q, right? You could just evaluate the formula I gave you, but that would be very inefficient. So what people do is they were able to derive this formula that may look a bit scary, but the point is that it allows you to very quickly evaluate how much would modularity increase if I take node I and move it into the group or community C. And this thing has the following terms. I will explain a bit, but I don't want to explain too much because this is your homework problem. Okay? But essentially, the parts of this that are important are this sigma in is the sum of the link weights, or the number of links between the nodes that are in the community. So this is kind of internal number of edges. Sigma total is the value of all link weights of all the nodes that are in C. So this means it's everything that's inside plus everything that points outside. And then I have, for the node I that I'm interested in moving into C, I ask how many links are pointing into the C, and then how many links total does the node have, right? This is for asking how much will modularity change if I take I and move it into C. what I also need to derive is the other side, which is how much will modularity change if I take node I and move it out of the current community, right? Because right now node I is member of D. I take I out of D and put it into C. So I need to account for this change twice, right? Taking it out and then putting it in. And this is only 1/2. This is only putting it in part, right? And then the delta Q is the sum of how much does modularity change when I take node I, take it out of D, and I put it into C. Okay? That's the idea. Now, a bit more inside, how do you derive this? Is the following, is that this equation has two parts. It has the modularity contribution before it's kind of the modularity before I put node I into the community C versus modularity after I have put it into C. And the way you can derive this is that you can think the following. You can say there are only three things you need to reason about. You need to reason about the node, you need to reason about the community, and you need to reason about the rest of the graph. And you can essentially think that your graph has three nodes. It has the community node, has the rest of the graph node, and has the node of interest I node, right? And now the weights of these nodes are, this is the number of edges from I to the community. This is K in. And then you can work out how many edges I has here, and you need to figure out how many edges are here and how many are here. And based on that, right, to the rest, from the community to the rest of the graph. And then based on that, you derive this expression. You will kind of follow this to do this in your homework. Okay? So this is phase one. And the point is, if I go back, this is very easy to compute, right? All I need is these two summations that I can cache in the outer for loop, and then for every node, this is what I need to know. And then there is, like, even though there are summations in here, there is no summation. It's just, it's a couple of additions and a couple of multiplications, and I'm done. So it's extremely fast to evaluate. Okay? So now this was the first phase. Now in the second phase, we do this restructuring, aggregation, coarsening, where the communities that we obtained in phase one are now contracted into supernodes. Each community becomes its own supernode, and nodes are connected if there is at least one node in one community that links to the other node in the other community. This will connect the corresponding supernodes. And the weight of that connection will be the total number of edges, or the total edge weight between the two communities that you merged into supernodes. And this will coarsen the graph. And then after you have coarsened the graph and created the weighted graph, now you apply phase one again. Okay? To even be more precise, I have the pseudocode for the algorithm, where this is phase one and that is phase two. But essentially in phase one, all I do is to say for every node, I go and ask what is the best way to take node U to move it into some community C, and I ask what is the best community to move it to when I go across the neighbors, and then if that's the case, I update these summations so that my modularity computation can be done very fast. So essentially this is just bookkeeping of this summation total and summation inside. So again, it is just the total degree of node U and the total degree of node U linking to a given community. So this is super fast to update, but this is just bookkeeping counts. And here I update the memberships of nodes to communities, right? I take this node and put it into community C hat, and I take it out of community C. If C hat is the community that increases the modularity the most for node I, and if no vertex makes a move, which means that the benefit is not greater than 0, I'm done, I stop, and this is the phase one. And essentially, again, all that is there is bookkeeping plus moving the node. And then in the phase two, I'm rebuilding the graph, where again, I'm contracting every community into a supernode, and then I'm updating these counts in terms of creating weighted edges between the supernodes based on the number of edges between the communities. This is when the phase two would halt, and then phase 1 would continue. And you would do this until everything is merged into a single node. Yes?
Is it common practice at all that you know like a certain number of communities, or you're seeking like a certain minimum number of communities to stop this process prematurely?
So the question is, how do you decide what is the number of communities to take? The best way would be to ask, I will take the number of communities, so I'll cut my dendrogram whenever my modularity is maximized. That would be one way to decide, right? But it's a clustering problem, so it's hard to know how many clusters you want to select.
Oh, I mean, if you have a target like cluster number, can you stop this process?
You could stop it when you found the right target, if this is really what you want. But the issue, I think, with that will be if you stop it, then this will determine the natural number of clusters, because you start with everyone being in their own cluster, and then people leave the clusters and clusters become empty. So you discover kind of the natural number. So this won't give you the best modularity for a fixed number. It will find you the best modularity for a natural number of clusters that this method discovers. Okay? And here is just another visualization illustration. I start with the graph. Every node, for example, node 0 would now ask, every node is its own community, so node 0, ask yourself, what if I join my neighbor number 2 into the community, my neighbor number 3 into the community, my neighbor number 5 into the community, and there is a mistake, there should be an edge between 0 and 4, so that would be what node 0 is asking itself, and then decides to join to the community that has the largest delta, and we keep iterating this. After there is no improvement possible in the overall modularity, we will converge to some partitioning. Based on that, we create the super nodes. For example, you take these green nodes, contract them. There is a self loop of size 16 because the total edge weight between these nodes here is 16. There is, for example, in this case, there would be an edge to the blue cluster of weight 3, because the sum of these two edge weights would be equal to 3. The green supernode also links to the violet one because of that edge. But for example, green does not link to orange because there is no edge between the green nodes to the orange nodes. Right? This is now my super graph. And then again, I would start the second pass analogously to here. Every node is its own community. Again, I would run this local improvement. This is where it would converge. And then again, I would merge these two and merge those two to come up with a graph like this. I could even run community detection here, and I would cut here, and I would decide that I finish with 2 clusters. Right? So things get trivial as things get smaller, but things get interesting kind of in this space. Okay? So this is what I wanted to show you. So let me just summarize. We learned what is the modularity metric. We learned it is the difference between the number of edges between a group of nodes minus the expected number of edges under our configuration model. And then we talked about modularity maximization method that is called LUN. That is this kind of greedy modularity optimization algorithm that does these local changes and then does coarsening to create this hierarchical community structure. So this is what I wanted to say about this topic. All right? Yes?
Since LUN is a greedy strategy, do we know how well it does on the global maxima? Like how optimal it is?
So the question is, this is a greedy thing. Do we have any notion how close it is to the maximal, to the optimal thing? Finding optimal community structure is MP hard. And I will talk next week on Tuesday about some methods where we get approximation guarantees. Here we have no approximation guarantee, but I would say in terms of what people run when they need to do something, this is by far, I would say, the most popular method people run because it's easy to use, scales, gives you the hierarchy, you can look at it and make a decision. Empirically, it works well. I think theoretically, there is no or very close to no analysis of it. Okay, yes?
How is it different from clustering?
How is this different from clustering? This is clustering. It's clustering of a graph where your objective function is not, I don't know, minimizing some distances or whatever you do in k-means, but your objective is maximizing the modularity. So this is clustering of the nodes of the graph with a very particular objective function. Okay, good point, yes?
So after each pass of the algorithm, you have a set of clusters. How do you decide when to stop those passes?
Great, the question is how do you decide? You don't need even Mac wants me to. Okay, you don't need to stop, right? You continue until you will be left with one community. So this thing will stop by itself. If you want to stop early, you can. But at the end, you will have 4, you will have 2. So you cut here, and then you stop. You are done. This is the end, right? There's nothing more to merge. You are left Yes.
So at that point, you're left with 2 communities.
Exactly. But then it depends. But then do I say that my graph has 2 communities? Do I say my graph has 4 communities? What you can do is compute what's the total modularity of this thing, what's the total modularity of this thing, and whichever is bigger, pick that one. So that's one option to do. Yes, let's do last one because I have some more to tell you.
After the step 2,
yeah?
we decide the edge weights between the supernodes. Is it the number of connections?
It's the total weight of connections, right? So here you think of your graph to be weighted, right? So it's the total weight, right? So for example, when I merge these two, it should be this plus this plus right? Like so here there are 3, so that's why there is a 3 there. Why this should be a sum of this plus that. This should be a sum of this plus that, and I think it kind of is almost right. But you just sum up the weights, and then if the graph is unweighted, everything is a weight 1. If you have weights, then you just sum them up. Okay, let me continue. Thank you for the questions. I have to tell you the last thing. So far, I talked about this type of picture. But what you can also think about is to say, what if these groups overlap, right? None of us is a member of only one group. We are members of multiple groups at once. So let me show you an example. So this is a social network of one of the students in my lab. Okay, this is their so every dot here is their Facebook friend, and the edges are friendships between his Facebook friends. Okay, and the question is, do you see any clusters here, right? What are the social circles of the student in my lab? Maybe you would say there's something here, there it seems a big mess there, and so on. It turns out the method I will show you will identify this type of clustering structure. It will say there are 4 social circles or social groups of my students' friends. Here they are. And you can even go and label them. If you go and label them, so this was a student in my group who's from Korea. So there were quite a few students, friends he has from high school. He also has friends at Stanford who he was playing basketball with. And then he also has friends at Stanford who he plays squash with. And then the company is friends from his internship. And what is interesting is, for example, that some of his high school friends are also at Stanford and he plays basketball with them. And then another subset of Stanford friends he plays squash with. And some subset, they were actually doing internships together at the same company, right? And one thing I want to show you is black nodes are nodes that only based on the network structure the method put into the correct cluster, and the white nodes are the ones that the method misclassified. So here the student would go and label each of his friends what community, what cluster they belong to, and you see that for majority of the nodes they got classified correctly. Okay? So again, the input is this, the correct output is that. Okay? And then the second thing I want to show you, these nodes are proteins, so molecules in our cells, and 2 proteins are connected if they physically interact in the cell. And the question is, can you identify communities or modules in this network? And if you do it, here are the modules, and here is how they overlap. Right? So you see that in some cases these modules overlap quite a lot. Some are nested, like this one is part of a bigger one, and so on and so forth. So you see this kind of hierarchical overlapping structure. Okay? So to contrast what we talked so far we talked about this view of the network, where you have these multiple groups that are linked inside strongly but don't interact too much. If you think of the adjacency matrix, this is how we think of it, right? I have nodes, green nodes link to green nodes, orange nodes link to orange nodes, and there's relatively few edges between green and orange. This is what this tries to say. In the overlapping case, it's much harder. In the overlapping case, this is how things look like, right? You can think you have two groups, and these are people that are members of both groups. So if you think of it from the adjacency matrix point of view, this is the structure, right? I have two groups that overlap. So here in the overlap, there is many more edges because you can be edges because of group 1 or because of group 2, okay? And you can now think of this as, in some sense, tiles overlapping, and the amount of edges stuff here is higher because it's the overlap of two tiles, okay? So now with that, let's decide how are we going to do, how are we going to proceed. So what I will tell you is we'll do this in 2 steps. First, we will define what we will call a generative model for graphs. And we will call this model AGM, for community affiliation graph model, right? So I will give you yet another model to generate random graphs, okay? But this model will be different. So after we will define this model, we will do what is called maximum likelihood estimation. What this means is that we will say, let's take a real graph and let's assume that my graph was generated by my model. So now I can say, what is the best version of my model? What are best model parameters that could have generated my graph? And by fitting the model, we will discover communities. The reason why we'll discover communities because the way this model will generate the nodes of the edges of the graph is based on the membership of nodes to communities. So essentially, we are making this assumption. We design a generative model. We assume that our data comes from the model, and then we say, what are the model parameters that could have generated the data? And the model parameters will tell us how nodes belong to communities. That's the idea. Okay? Let me show you now the model. The model is very simple. It will be this type of bipartite graph where on the bottom I'll have the nodes. Here they are. On the top I'll have communities, and a node is connected to a community if they are a member of it. Right? So the blue guys are members of A, green guys are members of B, and the red nodes are members of both. Okay? So now that I have defined this, I need to decide if somebody gives me this thing, how do I generate the graph? Okay? So if somebody gives me this bipartite network that tells me how nodes belong to communities, every circle here becomes a node, a circle in my network, and now I need to decide how to design the edges. And we will have one more set of parameters, which means that every square node, every community will have one parameter, let's call it P sub C, and this will tell us how likely are nodes of that community to link to each other. Okay, so now I have the model fully defined with a bipartite graph, and every square has a value between 0 and 1, a probability. Now I need to generate a network. First, I know how to put the nodes. Here are the nodes at the bottom, so I just throw them in. Now I need to create the edges. And the way I will create the edges is the following. I will say that nodes in a given community C connect to each other by independently with probability P sub C. So this is essentially an Erdos-Renyi random graph model between all the nodes who are in a same community. Okay? But then you can ask, what happens to the nodes that are in multiple communities, right? And nodes that belong to multiple communities, they get multiple coin flips, because for every community they have in common, they get a different coin to flip, right? So you can say, what is now the total probability that nodes I and J connect to each other? Here it is. Probability that nodes U and V connect to each other is, I will read it and then I'll explain. It's 1 minus a product over all the shared communities nodes have in common. It's 1 minus the probability of connecting under that community. And what this is really saying is the following. This is the probability that at least one of these biased coins comes up and says yes, right? This is the total probability of all of them saying no. not generating an edge, and 1 minus that is the probability that at least one of them says, yes, let's connect these two guys, right? So the more communities you'll have in common, the smaller this product will be, because these are numbers less than 1. So it will be 1 minus a small number, so the total probability will be greater. So the more groups you have in common, the more likely you are to be connected. Does this make sense? No? Yes? Okay, great. Thank you. Good. Everyone still happy? Yeah? Okay. So now with this, I can show you what this model can do. Right? If somehow somebody gives me this thing, I can go and generate a network, right? So for this particular 3-node community structure, here would be the underlying network where, the blue nodes belong only to community A, orange only to B, the pink 2 nodes belong to A and B together, and the red belong to all 3 communities, and then the green ones here only belong to C, okay? So, and this model has a lot of flexibility because it allows me to express many different types of communities, right? If I want communities that are non-overlapping, here is the membership graph, right? The orange belong to A, blue belong to B, and that's it. If I want overlap, then, I have nodes that belong to both, and they are here. And if I want things to be hierarchically nested, then I can do the following. This is the mother community that everyone belongs to, and then some subset belongs to A, and some subset also belongs to C. And this would be kind of the graph we could generate. Yes?
Just to be clear, you need to, in this case, know how many communities you want.
In this case, you would need to know how many communities you want. Exactly. Okay? So now I taught you how to get from the model to the graph. Right? We don't care about this. We care about kind of going the other way, right? We want to say, given the graph, find the model, right? And if we are able to find a model that generates our graph as closely as possible, we have just discovered who belongs to which community. Yes? All right, super exciting. So let's figure out how to do this, right? When I say find the model, what do we need to find? Is this graph. We need to find the number of communities, and then we need to find this community parameters P sub C. So let me tell you how are we going to do this. And if you haven't yet seen this, this is an example of what is called maximum likelihood estimation. So let me tell you how this works, right? So the question is, how do I estimate model parameters of my model F, right? So in my case, model parameters are these things, are essentially specifications of this graph. Right? How do I discover them? And the way I will do this is to apply this, what is called maximum likelihood principle, where I will be saying, I'm given a real graph, and my goal is to find model parameters, here they are, such that what? Such that if I take my model, use it to generate a graph, then my graph that I have generated is as similar as possible to the real graph. Okay, so I need to define some kind of similarity here. And this similarity that we will define is called likelihood. So the way we will write it is to say, how likely is my graph given my model parameters? Okay, and if I can measure the probability of my graph given my model parameters, then I can then say, okay, great, let me go over all possible model parameters and find the ones that is the most likely to have generated my real graph. Okay? So what do I need in order to do that? I need how to compute this probability. That's the first thing. And after I have computed it, now I need to know how to search over this guy and find the best one. Okay, these are two important tasks. So let me tell you, how do you define the likelihood of a graph? How do we define that probability of a graph given the model? This is now very generic, independent of the model. The way you can think of it is to say, here is my graph and here is the adjacency matrix of the graph. Conceptually, what you can think is that given my model parameters, model gives me some kind of randomized stochastic model, so every edge has a probability under this graph. Under this model, right? So now, how do I define my probability of graph given model? It is simply saying, I have these coin flips, here are the biases of the coin flips, And I can ask, what's the total probability if I take these coins and flip each one with the bias that's in the cell, and I get exactly this sequence of values? And the more likely am I to get this sequence of values, the more likely my model was to generate this graph. Yes?
So here, F is not a joint distribution. It's just a sequence of Bernoulli.
Correct. So now the question is, how do I do this? And the way we do this is we do it as a sequence of Bernoulli coin flips, or we assume edges are independent of each other. So I say the probability of a graph given my model is the product over all the edges of my graph, probability that my model generated that edge. And then I go over all the non-edges of the graph, and this is the probability that my model did not generate that edge. Right? So what is this doing? This is essentially going over all the cells here that have value 1 and multiplying those probabilities together. And then this part goes over all the cells here that have value 0 and multiplying 1 minus that probability. And all this is a total probability that my model has generated this graph under this assumption that each edge is generated independently. And this is a very kind of general way, but whenever you work with probabilistic graph models, this is how graph likelihood is defined. It's defined as the likelihood of all the edges that happened, what is the total probability of those, times the total probability of all the edges that must not happen, which is 1 minus the probability that they happen. Okay? That sounds good? Okay? So good. So this is now the principle. Now back to our model and to tell you how you actually go now do this on this concrete model. So the first thing we will do is we have this bipartite graph, but that's a very kind of hard combinatorial structure and it's very cumbersome to work with. So what we will do is rather than think of this as a graph, we will think of it as some kind of weighted complete graph. So this means that we will assume that every node has a row vector associated with it, where every component of the vector will be the strength of the membership of that node to that community. So if I have k communities, for every node I will have k values, where every value at position, I know, L, will hold the strength of the membership of that node to that community L. Right? So here the entry, if I have a vector f for node u, then an entry at position A will say how strongly is this guy connected to A. And an entry at position B will say how strongly is this guy connected to community B. And if the value is 0, then this node is not member of that community. Okay? So now what did we do? We transformed our problem into finding a vector f for every node, where the component of the vector measures the strength of the membership of that node to that community. Now with this, I need to go and define the probability of an edge to happen between a pair of nodes. So let me explain that. So the way we will define a probability of an edge is defined up here, and let me explain. So it will be 1 minus the exponent of the dot product between the membership vector of f of u and the membership vector of v. Okay? Why are we doing it this way? Because what is a dot product, right? If you have two vectors, you multiply their coordinates and sum them together. So if one of the coordinates, one of the entries is 0, then the product will be 0. So this product here will be non-zero only over at the communities where I and j both belong to them. Right? And then, so the total strength of the link will be proportional to the product of their memberships, and then we are summing this over all the joint memberships. So the more they have in common, the higher the number will be. If I take the negative and exponentiate it, I will get something very small, so it will be 1 minus something very small. So essentially, the more groups you have in common and the more strongly you belong to them, the higher the probability of connection. And then what is now the likelihood of my network that I observe? This is written here. So this expression is essentially that expression with only one difference, is that I never work we never work with products of small numbers because numerically that's unstable. So what you do, you take the logarithm. If you take the log here and here, then what you take is this product, you take it out, becomes a summation, and this is a summation of log probabilities. And this is called log likelihood. So here I'm showing you the log likelihood, right? So now I have a summation rather than the product over all the edges of my graph. Here is log of the probability of the edge, right? So this thing is exactly probability of the edge, and there's the log because I'm doing log likelihood. And then on this side, I have log of 1 minus, and because I have 1 minus the probability, this 1 will cancel, and then I have a log of the exp, which just means I'm left with whatever is inside, so that's why I have this here. Okay? So now I have the likelihood, and the goal is find f that maximizes this total likelihood of a given graph. Given that I'm out of time, I will stop here, but the next slide explains how to do this optimization. The way you do it is that you start with some random community assignments, and then you compute the best way to change the assignments that maximizes the likelihood. And this is called, you do this using gradient descent, and you are able to identify the memberships of nodes to communities, and because node can belong to multiple communities at once, you discover overlapping communities. So let me finish here. Thank you very much. One thing I didn't finish, sorry Michele, is I had these beautiful slides about what do you guys need to do for the project. So I'm really sorry. So let me do that quickly, okay? So that people who are on TV see it. So course projects are very important. There are different types of course projects, and students put a big effort into them, and we have a project poster session at the end of the quarter. We have examples on the website of what are good project proposals, what are good project milestones, and what are examples of good project write-ups. We require many times projects are a combination of some mathematical analysis plus some experimentation on the data. Results of the projects are typically result in kind of a write-up paper. Many of these papers are actually published at the conferences. Feel free to come up with your own project idea, that's preferred. But if you are struggling, come to us and we will help you. What we require you to do is write a project proposal that's 3 to 4 pages long, and team up into teams up to 3 students. You can also work in a single or a 2-student team. Best is in a 3-student team. What we would like? We would like a 20-word abstract of what is the core idea, what you are proposing. We would like around 1 to 2 pages of related work and critical assessment reaction to the papers you read. These are essentially about 3 papers that are related to your project idea. You read them, you summarize them, and then you critique them. There should be about half summary, half critique. This is important because the point here is to teach you how to think beyond what you read and don't take what the paper says for granted. And this will allow you to differentiate your work from what has already been done. And then in the second part, you then define the problem, talk about how does it relate to what you have read up here, what data you will use. Make sure that you already have the data. Please don't say, I will collect the data or I will crawl the data. It always takes longer than you think, and then you run out of time. So this is for your own good. We are very happy for you to use your own data. What algorithms, models will you use? Be as specific as you can. And then what is important is tell us how are you going to measure success? How are you going to evaluate, test your method? How are you going to determine that your method is great or that your method is not so great? See the course websites for examples of proposals. You can see all the projects from previous years to give you some inspiration. So thank you. With this I will finish. Logistics are register your group, submit by October 17th, midnight Pacific time. Please come talk to us if you need help. We are here to help you. Thank you very much. Sorry again.